Welcome to the lecture on section 4.2 in pre-calculus on the law of cosines. First, let's talk about where we've been in solving triangles so far. So we know how to apply right triangle trig identities to solve right triangles. We know how to solve SSA, AAS, and ASA oblique triangles using the law of sines. This is what we did in section 4.1. So of course SSA was the ambiguous case, which is the most work of all of these. Now we'll learn how to solve SAS and SSS oblique triangles using the law of cosines. So this lesson will be about this third bullet point here. First, let's try to understand where the law of cosines comes from. It's actually derived from the Pythagorean theorem. So if I look at my oblique triangle here in blue and I drop an altitude, a perpendicular, from one of the angles, let's just start with B, down to its opposite side here, I've split this side B here into this small piece, which I'm going to call X, and this piece here, the larger piece, which I'm going to call B, the original side length, minus X. So short one is X here, and the longer one is B minus X. So I've got two right triangles here, this green one and this pink one. Next thing I'm going to do is I'm going to write the Pythagorean theorem for the green triangle and the pink triangle. So I've done that. So this is your hypotenuse squared is equal to leg squared plus leg squared for the green one. This is your hypotenuse squared is equal to leg squared plus leg squared for the pink one. Now I'm going to solve each of those for h squared, since we have that in common in both of these. So I've solved them both for h squared. Now I'm going to say h squared is equal to h squared. So on one side of the equation, I will put this here, and on the other side of the equation, I will put this here. So now I have this equation here. And what I want to do is eliminate the x somehow so that I have an equation involving only my side lengths A, B, and C. So to do that, I'm going to expand this binomial and see what cancels. So I expanded my binomial here inside the parentheses. The next thing I'm going to do is distribute the minus. So I distributed my minus to all three terms here inside the parentheses. Everything else is the same so far. Next thing I'm going to do is solve for c squared. So c squared will be on the left. So what I have next, after subtracting everything over to the right-hand side, so I brought this negative over to the right, it's now positive. This a squared is already there. So this part over here looks like the Pythagorean theorem. Then I subtracted this one over to the other side, and I added this one over to the other side. This one was already there. All right, so the x squares are going to cancel here, equal and opposite signs. So I'm left with this here. So the last thing I'm going to do is I'm going to find a substitution for x in terms of a, b, or c, so that I can only have a, b's, and c's in my equation. So to get my substitution for x, I'm going to look at my pink triangle up here, where x is this side here. Okay, so x is the adjacent side to the angle C. So I don't want an h or an x in my equation here, such that I can end up with only lowercase a, b, and c, or uppercase a, b, and c in my equations here. I don't want x's or h's. All right, so I can say from that peak triangle that the cosine of angle C is equal to the adjacent side, x, over the hypotenuse, a. And if I solve that for x, I can say x is equal to a times the cosine of the angle C. All right, so that's what I'm going to put here in place of x. So I substituted for x in that last equation there, and I end up with my final form here where I've only got lowercase a, b, and c and one of my angles. This is called your law of cosines. Right? So basically what's going on here is that this is a general case, and the Pythagorean theorem is a special case of the law of cosines. So if you look at your picture up here, you can imagine if this angle C here was pushed over to here such that angle C was 90 degrees, you'd have the cosine of 90 degrees, which is 0. This part of the equation here would go to 0, and you'd be left with c squared is equal to b squared plus a squared. And that's what I mean by the Pythagorean theorem actually being a special case of the law of cosines. And you can develop the law for a b squared on the left and for an a squared on the left by dropping your altitude from the A angle and from the C angle and following the same procedure for each of those cases. So you have 3 laws that comprise the law of cosines. All right, just like you do have 3 laws that comprise the law of sines. So here's your law of cosines. So we've got the a squared law, the b squared law, and the c squared law. These laws are very symmetric, and they're actually pretty easy to memorize. So you've got your a, small a on the left side of all of this, capital A on the right, small b, capital B, small c, capital C. And then you've got your Pythagorean theorem set up here, and your subtraction correction, where these 2 lowercase letters are this one and this one, this one and this one, this one and this one. So these have a pattern, and they're not that hard to memorize if you're asked to memorize these, which sometimes you are. So we use the law of cosines to solve an oblique triangle that has SAS. That means you have 2 sides given to you and the angle in between. So you could have C and B given to you, for example, and you would be given angle A. All right? So looking at these bullet points here, as usual, we must be given 3 pieces of information for an oblique triangle in order to find the other 3. The SAS case will form one unique triangle, so we don't have to deal with the ambiguity that we had to deal with SSA. Notice that we cannot start by using the law of sines, because if we have a side and an angle and a side, we don't have a ratio that we can set up. We're not given the opposite side to the angle that we're given. So we can't start with the law of sines. So we need to start with the law of cosines. So we use the law of cosines to find the opposite side first, and then we use the law of cosines again to find one of the other angles by taking an inverse cosine, and then in order to find the last angle, once we know the other 2, we simply subtract using the angle sum theorem. So this is the process we go through for solving an SAS triangle using the law of cosines. So now, a word of caution. When you're solving the oblique triangles SAS and SSS, where these are your given pieces of information, there's a few points I want to make here. After using the law of cosines to find a missing side or an angle, you'll have a side-angle pair, tempting you to jump to using the law of sines to find the second missing angle, because after all, the law of sines is a shorter calculation. However, I don't recommend switching to using the law of sines for either of these 2 problems, because you can end up with a false solution which can go undetected. The false solution can occur when taking the inverse sine of a missing angle, if you're using the law of sines, because it'll give you an acute angle when you may actually have an obtuse angle. So there are 2 angles between 0 and 180 degrees with the same sine. All right, and that's why this can occur. This is a very common mistake to make And it's easy to overlook because the equations look correct. You can find the error that you've made by setting up the law of sines ratios, the three ratios, and noticing that they're not going to all give you the same decimal number, the same number. Therefore, since they will not, you'll have a false solution. You've got a problem. All right, in order to avoid this, don't go to the law of sines. Stick with the law of cosines, even though it is a longer calculation. That's because the inverse cosine will only give you one angle between 0 and 180 degrees. Therefore, you'll get the correct angle. You won't accidentally get the acute angle when you really have an obtuse angle. So you won't get a false solution if you use the law of cosines all the way through the problem. So this is what I recommend. So here's our first example. This is an SAS situation. So I'm given angle B, 32.5, side C, 4.9, and side A, 3.5, SAS, an included angle. All right, if I'm going to need to use the law of cosines, I can use the B law since I'm given the B angle. So I have A, C, and the angle B. I can solve for this B squared because I know everything on the left here. So I'm going to choose the B law from my law of cosines. So let me show you the page where I got that from. So I got it from here, the B law, which I'm going to use to solve for side B. So now I'm going to substitute in from my triangle those three pieces of information. So everything is substituted in on the right-hand side of the equation, and I get to type all of this into the calculator, and I'll get B squared. So you want to type all of that into the calculator to solve for B squared. All right, so be careful you don't make a mistake. You might want to run it through 2 or 3 times to make sure you get the same number each time. So I got this decimal number here. I'm just going to keep all of those digits. Remember, you don't want to do any rounding inside your problem until you get to your final answer. So if I take the square root of both of those sides in my calculator, I'll get B is equal to 2.7077. All right, so let me make a chart of what I still need to find. So here's my chart. So I still have 2 things I need to find here. All right, so my word of caution page, I said don't jump to the law of sines just because you know you have this pair here to set up a ratio. We're going to stick with the law of cosines. So I'm going to solve for C, angle C. So that means I need my C law. You could solve for angle A, but arbitrarily I'm just going to say I'm going to solve for C. So I'm going to write down my C law. So there's my C law. Now I'm going to substitute everything that I know into this equation. So I know all 3 sides. So here I'll have numbers. Here I'll have numbers. I don't know angle C, so this I'll leave big C, capital C. All right, I had to move my chart out of the way. It took up a lot of room. All right, so now I've got 4.9 squared. I'm going to subtract this from this side. I'm going to subtract this from this side. And I'll get a number for my left-hand side. And then I'm also going to multiply negative 2 times 3.5 times 2.7077. And I'll have a number in front of my cosine C. All right, and I'm holding on to all those digits. All right, so now I'm going to divide both sides by the coefficient negative 18.9539 on both sides. All right, so I typed that in. That cancels. And I typed in this over here, and I got negative 0.233638. All right, so now I can find the angle C by taking the inverse cosine of both sides. All right, so I'm going to be left with the angle C. So if I type that into my calculator, I should get the angle C is equal to this obtuse angle 103.5113. It's a good idea to put these angle symbols in your work here when you get to something like this answer here, so that you don't get it confused with lowercase c. It's just kind of a good habit to get into. All right, so I've got angle C now, and if I would have used the law of sines, I wouldn't have gotten that obtuse angle, and I would have had to be very careful that I caught that. All right, so if you ever have a negative in an inverse cosine, it's going to give you an angle that's greater than 90 degrees. Now, why is that again? Let's think. Okay, so what's happening is, back to something we know, if you take an inverse cosine, it returns you an angle between 0 and pi. All right, so this angle, let's say we have an arbitrary angle in the first quadrant and then one in the second quadrant where its reference angle is the same. Those angles will have the same sine value, so they will satisfy the law of sines whether you use this angle or this angle. But notice the cosine for the angle in Q1, the acute angle, is a positive number, whereas if you look at this obtuse angle in the second quadrant, your cosine is negative. All right, so we have positive cosine over here, we have negative cosine over here. So your acute angle will have the positive cosine, and your obtuse angle will have the negative cosine, but they'll have the same signs. And that's right there what the problem is with using the law of sines. All right, so let's put our list back up here so we can see what else we need. All right, so the last thing we need is the angle A. So we can just say angle A is equal to 180 minus 32.5 minus 103.5113, and you should get 43.99 degrees. Now, I haven't done any rounding there for, let's see, I did round side B. Let's just put that back here just for consistency's sake, and you can round according to the instructions in your problem. All right, so remember, we don't do any rounding internal to the problem. The only time you would ever do any rounding was after you've got all your numbers figured out. Then you decide which digits you need to round to, whether it's the tens, hundreds, whatever. All right, so that's SAS. Okay, next, the next law of cosines problem that we solve is your side problem. That means we know all three sides. So as usual, we must be given three pieces of information for solving an oblique triangle, and or our three will be sides in this case. So three sides will form one unique triangle, so we don't have any ambiguity in this case either. All right, we cannot use the law of sines because we're not given any angle side pairs, so we can't form a ratio to use the law of sines. So this is why this is a law of cosines problem. So we use the law of cosines to find the first missing angle. So we'd have to use inverse cosine again. Then we'll use the law of cosines again to find the second missing angle. And I'm going to make a note here: avoid the temptation to use the law of sines, which is a shorter calculation. Also, do not use it in an SSS problem, my recommendation, so that you don't end up with a false solution, because they won't give you the obtuse angle if you happen to have one. So then the last thing we're going to do is find the third angle by subtracting the first two that we found from 180 degrees, and then we'll have all six pieces for the side case. So in this problem here, side, I'm given all three of my sides, which I've written on my triangle. I'm going to set up my table here. So I've got the three sides. I need to calculate the three angles. So I can start with any one of the angles. So let's just start with finding angle C. So that means I'm going to use the C law for the law of cosines. So I'm going to write down my C law. So notice that I know all of my sides which I will fill in. The only thing I won't know is my angle C, which I can solve for. So I'm going to substitute in for what I know. So I've substituted in all of my known quantities, and I'm going to solve for the cosine of C. So I subtracted 26 squared and then 32 squared from the left-hand side, and I got 149. Then I got my coefficient for the cosine of C by multiplying these three numbers together, including my negative right here, and I've got this number here. So now I can divide both sides, and I'll get the cosine of C. And I get this decimal number here. All right, when I did this division here. All right, now I'm going to take the inverse cosine of both sides to find the angle C. So I'm going to type this in. So I'll have my angle C, and I end up getting 95.137 degrees. All right, so let's put that in our chart here, 95.137 degrees. All right, so now I have angle A and angle B left to find. So I'm going to arbitrarily say let's find B. So I would need my B law. So I wrote down my B law. Let's go ahead and do the substitutions. So we know everything but the angle B. So those are my substitutions of everything I know, all the sides. Now I'm going to subtract this number and this number from this number and put that on the left. And I'm going to multiply these three together, and that'll be the coefficient of cosine of B. And this is what I get. Now I'm going to divide both sides by negative 2336. And I get cosine of B is equal to 0.671288801. Now I take the inverse cosine of both sides. So inverse cosine of both sides, and I'll get my angle B is equal to 47 degrees, 47.8334 degrees. All right, so let's put that in our chart. And the last thing will be to find the angle A, which I can do by subtracting from 180. So let's go down here and fit that in, my very last step. So angle A is 180 minus 47.334 minus 95.137. And you should get 37.03 degrees. So this is angle A. So that's the last thing in our chart, 37.03. So here's our solution to our side problem. All right, so this concludes part 1 of our lecture on the law of cosines. We're going to do a couple application problems in part 2 of our lecture on the law of cosines.